Okay, let's get started. We're going to review a little bit, show some movies of different connection failures, talk about welds, and then get into eccentric connections today, is what we're going to start out with. Let's talk about stuff we talked about before. What is UBS? Who remembers? What's that all about? What's it for? What are they used usually for? There's some kind of area reduction factor because of shear lag, right? UBS is the U for BS, block shear, right? Yeah, that's what BS stands for, block shear. Yeah, keep telling yourself that. And what values do we use for UBS? 0.5 or what? 1 or 0.5, right? Those are two values. And when do we use a UBS of 0.5? What's the circumstance? Multiple rows of bolts in shear. Not any kind of shear. Well, let's say that. It's called out pretty specifically that it's multiple rows of bolts at the end of a beam in shear. Okay? That's what they're called out to. That's when you use a UBS equals 0.5, and that's when you just have to use the equations. Hey, when do we use it? Hey, we just answered that. Awesome. I'm going to remove this. Hurting me. Okay. Shouldn't hurt yourself in your job. Okay, now let's say I want to find the bolt capacity of something. How do I find the capacity of a bolt? Table, right? Table. Don't use an equation for the bolt capacity. If you try to look up the capacity of the bolts in the tables and use some equation that looks like phi PN equals phi area times 0.6 Fy, some number like that. Actually, they don't ever work. None of the equations for the given strengths in the bolts, this equation doesn't work. There's some other built-in safety factors that are in there. It's just much easier to go ahead and use the chart. Okay, so use the chart. I think it's table 7.1, but I wouldn't want to bet money on that. Right? Pretty sure it's table 7.1. When we have an N and an X in bolt design, what does that mean? What does an N mean? Threads included. An X means threads excluded. Which one has lower capacity? What? Included. N would have the lower capacity. Great. This is all stuff we've seen before. So boring, right? Let's talk about welds. We're not going to spend a lot of time at all on this handout. You should look at this handout on your own time because we're going to go through it real quick. When we talk about welds, it's just another way to hook two plates together. Oftentimes people, depends on the connection. Sometimes we like to bolt, sometimes we like to weld. Oftentimes we'd like to do as many welds as we can in a shop and as many bolts as we can in the field. But that's not always possible and not always done that way. There's different types of welds, fillet welds, which we'll be talking a lot about today, full penetration welds. And the coolest thing about the full penetration weld is that you don't have to design it. You don't have to design a full penetration weld. You just specify it. Okay? If you specify a full penetration weld and they know what the base metal is, they will use an electrode that will provide enough strength so that the load can be transferred. Okay? Now there's a lot of labor that goes into full penetration welds, and you should avoid them if you possibly can. When we were out on our field trip, we heard the gentleman talk about designs of the roof truss, and he talked about using a full penetration weld versus a partial penetration weld. He actually mentioned that he beefed up the members of the truss so that he could get away with using partial penetration welds instead of full penetration welds, because they're so much cheaper, so much easier to inspect, right? Now, that's not necessarily the best for fatigue performance. So we would much rather have a full penetration weld because it's very easy for that force to flow, right? It's much more challenging in this case for the force to flow here. There is air right here, right? There's air, and air isn't strong, right? Not in tension. Not in tension. Compression, sometimes. Anyway, never mind. So, we got some situation like this. Load going this way and this way, right? Whenever we make load move, then you're going to create stress concentrations, okay? And when you get fatigue issues, these can lead to that's where you'd expect to see the failures at, locally around these welds, fatigue type failures. But that doesn't mean we can't design these safely, okay? It can be done. We're going to be designing fillet welds in this class, and this is actually how you design most welds. There's lots of information. Maybe you've seen this equation before. I hate this equation. I can't remember it, okay? And if I can't remember an equation, then it's too complicated. Okay? So in this class, we've simplified this equation, okay? And we've narrowed it down to this. 0.02 times FEXX times D times L. Now, people will sometimes look at this equation and they'll get confused. They'll say, hey, there's no phi factor in it. I need a phi factor. No, the phi factor's there. Remember, it came from this equation. We've simplified it. We've multiplied all of these constants together. We've simplified it. And for an equal leg length weld, this is the way to design it. And almost all welds are equal leg length. At least almost all of them are designed. Doesn't mean they're always constructed as equal leg welds, but they're designed often as equal leg welds. And if they're not, you would just change this term right here depending on what your geometry is. Alright? So it's not like it's that big of a deal. So FEXX is the yield strength of the electrode. D and L. D, this is a little confusing at first, but once you get it figured out, it's not that big of a deal, is the leg height in 16th inch increments. Okay? So if I say something is a 3/8 inch weld, or here I have an example where it's a 1/8 inch weld, that's the same thing as 2/16. Okay? My D is 2. Why? Because it's the length in 16ths of your leg height. Okay? Okay. L is the length in inches. Okay. So I took 0.02 and I multiplied by 70. I multiply a D of 2 and a length of 5, and I get 14 kips. Okay? 14 kips. Now I have a lot better ability to remember this equation than I do this equation, and that's why I use it. Okay? And that's why I suggest you use it as well. Another rule of thumb is with an E70 electrode, and what this really is saying, you can simplify this even further in case you forget this. With an E70 electrode, you can say you get 1.4 kips per 16th inch leg height per inch in weld length. Okay, so if you don't, this doesn't make sense to you what I'm saying here, you can use this equation. This is just a further simplification. It's the way I like to think about things. 1.4 kips, almost a Toyota Corolla, per 16th inch of leg height per inch of length. Okay? Okay? It's a lot of load. It's a lot of capacity. Now, they have all of these things down here that we're not going to talk about. These rules. You have all these rules with welds. Okay? Not that hard, not that big of a deal. You have all these rules with welds, though, about minimum leg height, maximum leg height, all kinds of end radius stuff. And we have this beta factor. This beta factor is a term that takes into account, we're assuming that when we load this weld to failure, we're assuming structural resiliency happens. We're assuming that we may overload it locally here and locally here at first, okay, at first. And it may reach yield at those two locations at first. And you probably don't believe me right now, but it's true, okay? There's lots of ways you can prove it. You can think of, we won't talk about it, but it's true for now, okay? It may overload, but then this will pick up the extra load and pick up the extra load and pick up the extra load, and it won't fail until everything is at its limit. Does that make sense? That's the concept, and that's the idea. Welds are brittle material, all right? There's a huge safety factor built into welds. Massive safety factor built into welds, all right? Same thing with bolts. So we really, really, really don't want a weld or a bolt to fail. Okay, we really don't want that to happen. And that's some of these things, some of these rules help us get out of these safety factors, and hey, this one does as well. You know, we assumed everything is yielding at the same time. Okay, we assumed that it all yields at the same point. That's the way we design things. Okay, in very, very, very long welds, because the welds are so brittle, that may not occur. Structural resiliency may not be able to occur. Okay? We may not be able to get the strain and ductility that we need to out of our connection. Okay? So because of that, we put another safety factor on top of it. Okay? Now, one could argue that possibly what you should do is load the system up, calculate what the actual strains would be here, calculate what the strains would be here, see if you've exceeded what your strain capacity is for your weld, right? Double check that. That's kind of what we do in reinforced concrete. We look at over-reinforced beams or not, okay? We're doing similar type of calculations, okay? They've decided, though, in structural steel that they're not going to make things that complicated. Instead, they're going to focus in and they're just going to reduce the strength if your weld is long, okay? Another thing that they're worried about here is they're worried about imperfections. They're worried about if your weld is long, the probability of an imperfection becomes much higher. Okay? And all you need is one imperfection that's not caught, and that will greatly, greatly decrease the strength of your weld. Okay? So this is to handle both of those situations. Okay? And oftentimes what people will do is they'll try to use things called stitch welds. Okay? And what a stitch weld is, if I'm hooking two plates together, I have welds that look like this. Okay? Two plates together. And if you're ever at stadium here on campus and you're walking up and down the stairs, whether it's the basketball or the football stadium, you look up on the stairs, you will see stitch weld, stitch weld, stitch weld. You often see a lot of stitch welds all over the place. You really start to look for it. And the reason why is because people don't need that entire length of weld to get the capacity. They're so strong. So instead they use stitch welds, okay? Individual welds together, much easier, okay? There's problems with stitch welds. Every time you start and stop a weld, it's not the best material, okay? That provides more of an opportunity for fatigue failure, all right? But that's, you know, there's plus and minuses, all right? And that's what people commonly use. Now, right now, the way this equation is written and the way it's written in the AISC code, stitch welds, once one has a stitch weld, you would use this as your L, your length of your weld. You would use your W as the I think that's the leg height of the weld, okay, that you actually compare it to, and that your beta is never going to control with a stitch weld type situation, okay. I don't know if that's what AISC intended, for people to be able to start using stitch welds to get away from using this beta reduction factor, okay, because it doesn't quite make sense to me that if I leave a millimeter gap between each weld, all of a sudden I don't have to pay attention to this anymore. Does that make sense what I'm saying? I don't think that's fair. But that's the way the code's written right now, and that's what people are doing. In their defense, beta factor didn't always exist. Okay, there's many, many years where there was no beta factor in the code at all. Okay, so who's right, who's wrong? I would, in cases where I'm not certain, I don't feel comfortable, I try to be conservative, all right? And if I have a long line of stitch welds, I would still use this beta factor, okay? But that's kind of a judgment call. Does that make sense to what I'm saying? I use a beta factor on the group capacity. Right? Okay. Oftentimes when you look at welds in different directions, this is another semi-new addition, at least from when I was in your shoes and taking a class like this for the first time, and to this point, this is a modification for the code that the weld people are always looking to get every part of the market they possibly can. They're tired of losing money to the bolt people, and they said, you know what, we're designing all these welds to fell and shear, okay? Right? They're all designed to fell and shear. But what if we have welds in tension? I'm sorry, yes, this would be welds failing in shear, pardon me, in shear, and this would be a weld failing in tension, and this would be another weld again failing in tension, right? That would have to happen, right, for that system to fail. And they find that actually welds in tension are much, much stronger than welds in shear. And it doesn't have to do with anything except for, if you recall, it's very common to look at the shear capacity of something. If I want to know the shear capacity, it's 0.6 times Fy. 0.6 times Fy or Fu. It's very, very common to use that. And it's actually, if you look at the math, it's like 0.588. It's from Moore's circle, all right? But people end up using 0.6, okay? It's a nice round number. Easy to remember. So they use 0.6 times Fy to find the capacity of the material in shear, and if it's in tension, it's just Fy, right? It's just Fy times the area, right? Times the area. Okay, so you know what? I see there's all kinds of ways one could have come up with to handle this, but they try to make themselves as designer friendly as they possibly can, and so they use this nonsensical equation. Okay, I mean, I guess it makes sense. The answer's right, so how can I argue with it, right? The answer seems to be conservative and it's easy to use, so how can you argue? And that's kind of their argument, all right? And what they do here is that as your angle between your load and your weld changes, then so does your capacity, okay? So when you're loading in pure shear, you get a multiplier of 1. When you're loading in pure tension, you get a multiplier of 1.5. 1.5. Well, if I have 6/10, which is the same thing as 3/5, right? And I invert that, right? It's what? 5/3, right? Which is like 1.67-ish. You with me? So 1.67 is what you should strictly be able to get if the welds were purely in tension, and that was a pure, straight change of that 0.6. All right, and they're a little bit conservative here at 1.5. You with me? Okay, well that's what they do. And this makes things interesting when welds start to be used with multiple angles. Okay, if I might have welds in tension here, or in shear and in tension, and we have to use an equation like this to handle it. We could talk about, well, let me just tell real quick, in case you don't recall where this equation comes from. We actually have two equations, and this is one where you can either add the pure shear strength and add the pure tension. And the reason why they use this, they allow this equation, it doesn't quite make sense. I mean, here we're all spending all this time and energy trying to figure out what the welds are in shear and tension, and then we come down to the end and we just say, you know what, act like there's no modification factor. Act like this isn't there. Act like this equation is 1 at the top. That's what they're saying here. And the reason why they allow this to happen or do it this way is because that's the way they always did it. Okay, they always assumed that welds in shear had the same welds in tension had the same capacity as welds in shear, because it was just easier, right? It's easier. You multiply the length of your weld and you're done, right? It's easier. But then they said, you know, if you want to take this into account, well, we're not going to let you have the full capacity of it in shear if you're going to take the breaking capacity in tension, and that goes back to some of the things we talked about with block shear. This idea that localized yielding. We have to ensure that we're able to get localized yielding out of these materials before we're going to rely on the full breaking strength of this material. It's a weld, it's brittle. You with me? Great. there's that. You know what? I have some other notes here at the end that I tacked on that are about design. Actually, how to design connections. We're not going to talk about any of them. Okay, but they're in there if you are a masochist and want to read them, right? Oh, no, you should read everything I give you, no matter what, right? So, just a couple more things to look at. I think we've now talked about every one of the failures, and we'll go ahead and watch some movies on them, because movies are fun, right? It's kind of cool. This is the same ones we showed before on the side, on the front, and at an angle. This is bolt shear. We're loading. Pops the head right off. Okay? Pops the head off the back. Watch that again. Again, this is a very brittle failure, right? You're loading, we're loading, the connection's giving, the bolts are going and bearing here. Boom, boom, pop, pop. See that? Yes? Okay, well, the scary thing is in a big connection, I'll try to bring in a video of a large bolt test that I went to see. And the scary thing about that is as you're loading and loading and loading, it'll break just like that, and all the heads will fall off like that. But we had some plexiglass around it, right? So it hit the plexiglass and fell down, right? Not that big of a deal. When the bigger the bolt, the harder it shoots, and the further it shoots, okay? And it's like gunshots going off, all right? I mean, there are huge bullets flying through the air when these things actually break in real life, okay? And so the one I'll try to bring in, you're watching, nothing's happening, it's looking great, then all of a sudden it's just like, wham! And like all the bull heads just shot everywhere, okay? I mean, it's pretty scary, all right? Okay, so we've watched block shear in the past. We watched fracture. I think we watched yielding, haven't we? Come on, baby. We watched fracture. We've watched yield. So we'll watch tearing. Okay. Oh, that's cool. Watch it again. So we're loading. The bolt's really close to the edge. It's very, very close to the edge, and I want you to watch here and here. There's no real warning at all. All of a sudden, just you can start to see a little bit of a fracture there. There it is. More of a fracture. Breaks all the way through. Okay, and then let's go to bearing. I'm not sure which one is the cool bearing, so we'll watch this one. That actually is pretty cool, and we'll watch that one again. What's going on here is, well, we're actually starting to load, and eventually we snap the head off the bolt. Eventually. As we load, I'll pause it whenever a major event occurs. Okay, so we can already see this bolt's just chopping right through this steel. It's just cutting right through it. It's bearing. There's localized buckling going on right here on this bottom surface that we can't see very well. As we keep going, now the plate starts to lift up some off the back. We've really starting to elongate out the hole. Yeah, you see that? That's the top of the hole. That used to be next to the nut to the shaft, right? You can start to see the top of the hole come out. We're going to start to see this lift off the surface. Oh my gosh, look, we can see right through it. Okay? Oh, didn't break for whatever reason that time. We'll do this one. bearing 2 we watched before. Okay, so we can start to see this color change. Well, this color change is the plate coming out of the plane coming towards us. Okay, we'll start to see it over here on the far left. Bending up, bending up. So anyway, let's see, real quick. Can I borrow your notes from last time on bearing and tearing? I have one. Oh no, previous to that. One thing that we were talking about at the end of class last time that I didn't get a chance to finish was when we were talking about these bearing and tearing calculations, and showing the video made me think of that just for a second. I think these are pretty straightforward. We have these equations that we're going to end up using. One's going to talk about tearing, one's going to talk about bearing. We use this L sub C distance. This is the distance from the edge of the hole to the back, and that distance determines everything, and hopefully that makes sense. Is it going to tear out or is it not? Right? That's basically what it comes down to, and you compare that to the bolt diameter. Well, one thing that we have to remember, this seems really simple and trivial, one thing we have to remember is that we need to do these type of calculations for every single row, okay? And possibly in both directions. Possibly for bearing and tearing in this direction, and possibly for bearing and tearing in that direction. Possibly. Unless one can use their logic, right, to determine that one is not going to control over the other one. Okay. So I've done that here. I've done, if we notice, a calculation for one bolt, and then in a sense, in the bottom I'm going to multiply by 3. I do a calculation to figure out what the tearing or bearing capacity would be for one bolt in that row. I do another calculation for what it would be for one bolt in that row. Okay. And I do another calculation for what it would be for one bolt in that row. And then if this is the key point, is I take first number I got for the first row and I multiply by the number of bolts in that row. And I add it to the second number and multiply the number of bolts in that row. The third number and multiply the number of bolts in that row. And this is really important. You don't just add these numbers together. You don't just find the lowest between 3 times this, 3 times this, and 2 times this, because you're only looking at failure of one row when you do that. Okay? And if one row fails, is the whole thing going to fail? No. That even your thought at one row could fail by itself is wrong, because structural resiliency is going to tell us that if one row gets close to failure, the other ones are going to start helping out more, right? Right? And they're not going to fail until they're all at their limit. Does that make sense? Okay. Okay, I tell you what, I have been looking forward to this point since the start of the semester, because for the first time we're covering new material. Oh, do you feel the goosebumps? Oh, I do. Do you feel the goosebumps? And this is a heavy audience participation part of the lecture. We'll have more audience participation coming up, all right? But this is one that it's going to be verbal. Don't worry, we won't be physical just yet. That's coming. But I'm going to need your help today. We're going to talk about eccentric connections. And that's really a connection that is not loaded through its center of stiffness. Okay? Not loaded through its center of stiffness. So if we have a connection like this, is that eccentric? Yes, it is. Sure it is. We don't even have to know anything about the bolts, and there's eccentricity there, right? There's eccentricity between this load and this load. Are you with me? Yeah? And that is an eccentric connection. And because of that, that's going to cause bending right here, isn't it? Yeah? Right? And it's going to cause bending right here, isn't it? Right? Because the connection's going to want to be straight, right? It's going to want to rack until it's straight. It wants to. It's want to bend. But these eccentricities are usually very, very small and oftentimes ignored. Okay? Almost always ignored. Okay? Only times I would be concerned about this is if I'm dealing with very thin plates or if my E gets to be very large. Alright? And those are kind of feelings you have to have. It's good to draw things to scale. It's good to look at things in AutoCAD that have been drawn to scale and say, does that look like there's a big E, a big eccentricity there? And if there is, then you might want to do some of these calculations, all right? Okay. But this is not what we're going to be spending the majority of the time on, all right? This is eccentric, but this is not what we're spending the majority of the time on. So let's talk about this connection versus this connection. Is this connection a concentric connection or an eccentric connection? We're going to assume that they're all in the same plane. Maybe it's a sandwich plate, right, on the top and the bottom, and with one in the middle. So what was the definition I gave? A connection that is not loaded through its center of stiffness. Where is the center of stiffness of this connection? Between the bolts. Where at? There's a lot of spaces in between bolts. The horizontal plane. And I'd even go even further than that, Jacob. I would say that that point right there is the center of stiffness of the connection. Okay? You could almost think of these bolts as you could find the centroid of these bolts. Right? The centroid. And the centroid of the bolts would be here in the connection. And that's used to be what we do. Oh, you should be so thankful. So thankful that we don't design eccentric connections like we did when I took this class. Oh, man. It didn't make any sense. It was really hard and took forever. And now it makes sense. It's easy and it's short. Sounds like improvements to me, right? Now let's talk about this type of connection. Is this an eccentric connection? What do you think? What's the definition? Does the load go through the center of stiffness? Does it? No. No, it does not. This is eccentric. And this is what we would call a concentric. Okay? And it's all about this center of stiffness. It's all about this center of stiffness. And because this load goes right through the center of stiffness, it's concentric connection. Because this load obviously does not go through the center of stiffness, and that's an eccentric connection. You with me? Okay, so you need to be able to notice on your own whether things are concentric or eccentric. Okay? I'm not going to tell you. You're just going to have to figure it out. Now, you have to look at this. And when we worked this problem, what was the load we assumed were in each bolt? What's the load in this bolt? Hit your button and tell cyberspace for me.
P over 6.
P over 6. P over 6. Each load went in that direction, and it was equal to P over 6. Yep. Yeah? Okay. Where's the load going to be here? Is it? Or here? Or here? Or here, or here, 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 all over the place. What's it going to be? It's not as obvious. It's not as obvious. Okay, and it's, how would you work a problem like this? Well, believe it or not, every one of you has seen a problem exactly like this. Exactly like this. You just saw it in a little bit different way. And it's another thing you're going to learn in structural engineering is that You need to see similarities between problems. So stay with me here. I say this is a complicated problem, but you have seen it before, and we're gonna use another analogy of stuff you've seen before. You've done cantilever beams, right? Yeah. Hopefully, at some point in your life. Jennifer, have you done a cantilever beam? Yes. Good. That's excellent. So I have load P, right, on my beam. What's my shear diagram going to look like? Is it 0? Is it triangular? No. It's constant. It's constant all the way across. Okay? What's my moment diagram going to look like? What do you think? First it's negative. What's it got to be at the tip? 0. The integral of a constant is a line, right? With positive slope, right? We're drawing a line with positive slope to hit 0. Yeah? Yeah. And this would be equal to P times L, whatever L is, right? That'd be the moment. Great. Now, if our cross-section looks like this, what stresses do we have on that cross-section? This is the part where you have to really help me here. What stresses do we have on the cross-section? What stresses are there? Axial? No. Not pure axial, not P over A. What else? What else?
Bending.
Bending. How do you calculate bending stresses? What's the equation?
Y over I.
My over I. And those stresses are normal forces, right? They're forces that are perpendicular to the face, right? So we're going to have compression and tension, right? Compression on the bottom, tension on the top. Coming in and out of the page. You with me? Are there any more stresses on that cross-section? Shear. What is the equation for shear? Tau is equal to what? And don't tell me V over A. That is dead wrong. What's the equation for shear? Anyone remember? IT or IB, that's right. 12th man is proud of you. Good job. VQ over IB. Pistol Pete is sad about all of you. VQ over IB. Just kidding. So these stresses, where do they happen at? Are they normal forces? Do they happen in and out? No, they happen in the plane, don't they? Right? And you will actually find that they actually happen as a parabola, right? And they're high here, and then they get low and low, right? Stresses look something like that. Remember that? Kind of, sort of? VQ over IB. Great. Awesome. Thank you for your participation. I need a little bit more. What happens if instead of loading in the center of my circle, my tube, my bar, what happens if I move it off E to the side? You get torsion. Exactly. So, are we still going to have bending? Yeah, we don't get to, it doesn't get to go away just because it goes to the side, right? So we're still going to have bending. We're still going to have My over I, and it's still going to be coming in and out of the plane. Are we still going to have shear? Does it get to go away? No. No, it doesn't. So we're still going to have VQ over IB or IT. And David is exactly correct. We're also going to have torsion. Okay, so this was shear. This was bending. And this was torsion or torque, whichever one you like to call it. And there was no torsion up here, but there is torsion down here. And what is the equation? Anybody remember? Anyone remember the equation for torsion? There's a torque in it. TR over J. TR over J. Right? Where J is the polar moment of inertia. Remember this? It's combined stresses, that thing you did at the end of strengths, right? That you forgot about, right? Now, the cool thing is, the thing that the most important, well, one important step that we need to realize is that where does this stress happens at? It happens in the face, doesn't it? Do you remember that? Do you remember that? Where does this stress happen at? In the face. It happens on the surface. Okay? Happens on the surface. Okay? So here it's going to be going here, here it's going to be here, here it's going to be up, and here it's going to be over. It's a continuous, it's like a clock, right? So when we have these stresses, in some places, these stresses are going to add. Do you see my stress from my shear and my stress from my torque and how they add together? Yes? And do you see in this location, they're going to subtract. You with me? Well, what's my shear stress here? It's 0. So there's no shear stress. There's just torque. And what's my shear stress here? 0. Remember that? Remember that? It's been a while. So what this means is that in some places, these two stresses will add. In some places, they'll subtract. In some places, this will be 0 and this will be positive. And in some places, this will be 0 and this will be negative. We don't really care about positive or negative. It's still stress. Oh my God. It's still stress, right? Okay. So, and that's kind of what I'm explaining here, talking about here. Do you guys remember this stuff? Okay, if you don't, crack a book. Okay? Type in a website, all right? Because you need to remember this stuff. So now, what does that mean for B? And I flipped this over. I used to try to do this in this small space, but it just wasn't enough space. It just wasn't enough space. So let's say I have this connection. And if you think about how we worked this problem previously, when we talk about all these stresses over here, we would calculate the state of stress or the addition of stress from shear, and then we'd either plus or minus torque to that. Remember that? Right? But we need to it was very important to understand or keep track of where the vectors, which direction the vectors were going in. Right? Because that determined whether we were adding or subtracting, or the one was 0 or it wasn't. Make sense? Okay, so we're going to do the exact same thing over here. We're going to take this problem, and the simplest way to think of it or break it up is we're going to break it up into two separate set of forces, just like we did in the last one with a stress, a shear stress, and a torsional stress. Okay? So we're going to take this problem, and we're going to break it up into an equivalent shear load of P, okay? And then we're going to break this up into an equivalent moment of what? P times E. You guys okay with this? Okay? So when I talk about equivalent loads here, and at first we're just going to talk about from these individual loads, okay? Just from these individuals, just from shear or just from the bending. What are my loads and my bolts going to look like? And this is where I really need your help because we are running out of time and I have to finish this today. Well, they're going to look like they're in shear, aren't they? I guess I don't have to finish it. There's no reason to hurry through something. right? Yeah? You've been doing this forever, right? What are the stresses going to look like here? That's a good answer. Okay, so first of all, we have to think about which direction our moment's going, right? And we would think our forces would have to go in the opposite direction. You agree with that? Yeah? You agree with that? And we'd also think that we'd also go from the center of stiffness, right? And every one of our loads we would assume to be perpendicular to a imaginary line drawn from the center of stiffness to the center of bolt. You with me? You guys okay with that? What's the magnitude of each one of these? Not necessarily. I can see where you'd want to say 1/6p, okay? And we're going to find that that's ultimately is the answer, all right? But we're not there yet. We got to get to some other places first. We have to think elastically for a second. Okay, elastically, we would think that the value of each one of these would be a ratio of the distance from the centroid, right? The further they're away from the centroid, the larger the value would be, right? Yeah? We'll stop right there.